Okay, so let's start. So the last formal talk of the afternoon is by Emre Yolcu from Carnegie Mellon, talking about weak versions of extended resolution.
Yeah, so like the title suggests, these will be weak versions, whatever version means here, of extended resolution that are still, yes. Oh, okay. So that are still going to be reasonably strong, and those are of a similar flavor to Jakob and Niels' talks. They looked at systems that are on the higher end in terms of the strength. I will look at systems that are on the lower end in terms of strength that are still stronger than resolution, and we'll be able to do interesting things. So I will move a little bit quickly through the preliminaries because most of this has already been covered. There's one disclaimer though, there will be a lot of acronyms in the talk for those proof systems. Try to ignore the acronyms, but I have to refer to those systems by some names, so they are unavoidable. Okay, so resolution is the system that we will build our systems on top of. Resolution, you know, refutes a propositional formula in CNF form by using this single rule to derive the empty clause. And in case that is confusing to some people, whenever I say proof, I actually will mean refutation throughout this talk. And so an example resolution proof of this formula, for instance, might be arranged in a tree-like fashion, or it can be written down like a sequence. For this talk, it will not make too much of a difference because I will be informal, but I want you to think of this like a configuration proof where you expand or contract the set of the clauses. So you add stuff and then remove stuff from a CNF actually. And look, so the configuration version of this sequence like proof would be you start with the empty configuration and then you add this, you add this, you add this. At each step you have a CNF and you add these until finally adding the empty clause. So yeah, an extended resolution is an extension of resolution where at any step you can derive the three clauses expressing this, where P and Q are arbitrary literals and X is a new variable. I say P and Q are arbitrary, but for refutations they're without loss of generality going to be the previously occurring literals in the formula. They can themselves be previously defined extension variables, so X is going to be new. And yeah, in this talk I'm going to consider the relative strengths of weakenings of extended resolution, again, whatever that means. And since I might run out of time, because I always do almost in talks, I want to show you the results first. So those are the systems that we're going to be looking at. Okay, a lot of acronyms. So this minus indicates some weakening of the system. So without the minus, all of the systems that you hear, first of all, each node is a proof system built on top of resolution. And I've played them out a little suggestively here, but we'll come to that. So the minus indicates a weakening. Without minus, all of these are equivalent to all of Jakob's systems that you've seen. So on top of resolution, this BC system is the weakest among all of those. And now think of having three axes here along which you can generalize this BC system. Here you add something to the system. Here you add another thing to the system, which is orthogonal in that they can be combined and added together to the system. Along this axis, you add something else, again, which can be combined. So for instance, the system that you see here can be thought of as a marriage of this one and this one. Okay, so also moving out from the origin, you generalize the system. And an arrow from a system to another means that one simulates the other. So you have simulations going in these directions and these directions that are trivial, like this is trivial as well. And so this is trivial as well. And the point of this work is to look at the weakest generalizations of this BC minus system, which is a weak version of extended resolution, and show that, okay, they're all incomparable. They're qualitatively different, so they're quantitatively different as well. And so what about the colors? The black arrows were already known, mostly due to Buss and Thapen's work. The red arrows, so this distinction between red and green is for people who might have seen a previous version of this talk. The red arrows are the new results relative to the existing state of knowledge before the earlier talks. that I gave on this. The green arrows are the new results since the last time that I gave this talk. So I had like 2 open questions. Those are no longer open questions about the relationship between this system to these systems. And I needed a lower bound on this system to have those relationships. So basically the entire picture of those weakest generalizations is now resolved. And the point is less about those systems and more about the way you achieve those. They're all going to follow a simple recipe, almost like a cheap trick for proving the separations. And I will repeatedly use it to get separations in all of those ways. Okay, and still to appreciate that you don't need to know about the details of those systems, although I will try to tell you a little bit about them. So any questions at this point?
SPR minus versus SPR minus?
Yes, this is the system for which we have no lower bounds so far. So, okay. And so why care at all about this system? Well, they correspond, or at least the reason I care about this is different than Jakob might care about these systems. So for me, they correspond to being able to say in your proof the words without loss of generality, assume blah, 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 without needing to introduce new variables. So extended resolution can already do this kind of reasoning, but it can do much more as well. Let's say you want to study the weakest systems which still support this kind of reasoning, but do not have to go all the way up to extended resolution because you want to do proof complexity this time. You want to prove lower bounds or separations between them, while still being strong enough in that, again, this mostly follows from Buss and Thappen's work. You have upper bounds for all those hard tautologies in this SPR system. Some of those are not so interesting, but so from this point on and here and then out of the wall, the systems start to get interesting. Okay, so for instance, you cannot exactly do this, but effectively in those systems you can say, if I'm trying to prove the pigeonhole principle without loss of generality, pigeon n+1 is mapped to whole f. You don't literally say this, but you say something close to this and then you derive this in those systems. Okay, any questions? No. Okay. And like you saw in Jakob's talk, this is based around the notion of redundancy, where you derive things that are not necessarily implied, but just preserve equisatisfiability when you add them to the formula. So you'll have your formula gamma, which is a formula in the configuration, let's say, and you want to add a clause to it. And if it's redundant, you can add it if your goal is just to refute the formula. And this notion of characterizing the redundancy is helpful for obtaining various parameterizations of those systems. Again, you saw this in Jakob's talk, but let me go over it again. So we say a clause is redundant with respect to a formula, gamma, if and only if there exists some partial assignment such that this holds. So Jakob gave a more technical explanation for this characterization. I like to think about this a little bit more intuitively in that if this holds, then you can say without loss of generality C. So why can you do this? Suppose you are writing some informal proof. You have some lines. At some point you say without loss of generality C. Now you cannot just continue. You need to justify this step that you've made. And the way you justify it is you reduce the proof of not C to the rest of the proof with C assumed. Okay. So here what you do is, okay, I will not explicitly prove this, but you're saying I will prove this from this point on. Well, you will prove this is unsatisfiable. If this is unsatisfiable, then any restriction of it is also unsatisfiable. But if the other case here actually implies this, then just by proving this, you also prove this is unsatisfiable. Okay, so this is the way, at least I like to think about this corresponding to being able to say without loss of generality. Any questions so far? And of course, that previous notion involves implication, so it doesn't give you Kullmann proof systems. Yes.
So when you introduce this new C, is it allowed to also introduce new variables?
Yes. So far I said nothing about what C can be. That's the way. So we will first generalize extended resolution, and then weaken it back down to get systems between resolution and extended resolution. So yes, here the C could be just one of the clauses corresponding to the extension. Okay. So,
Emre?
Yes.
I like that explanation a lot, but it's sort of, you're implicitly using also that this implication is something that is simple that we can verify, right? And
yes, so far we don't have
the way to think about it is, okay, let me first assume C and then do the proof. And they say, oh, what if not C? Well, here's an easy reduction to what we did before. Kind of.
yes, for that reduction to be easily verifiable, you would need to use a restriction of the MTL. And that's where these actual processes will now come in. So we will use syntactic criteria that will automatically justify that relationship holds. It may not be obvious how this definition actually corresponds to the thing that I've just shown, but soon I will use how this ties together with that. But let's parse the definition together. I will show you more definitions, but this is the only one that I want you to be able to follow because it's the simplest one. And I think it's reasonable, although it's late. So a clause of this form, which includes a distinguished literal X or C prime, is blocked for X with respect to a formula gamma if for every clause that contains not X in the formula, if you had resolved this clause with all of those clauses, they all would be tautological. So this is also the motivation for why this was called blocked, because like it's blocked with respect to taking resolvents upon that literal. So if you have such a clause, then adding it does not change the satisfiability status of the formula. Okay, so the definition is clear. So, okay, and by the way, tautological means some literal occurs both positively and negatively. Here's an example. So this is the formula, this is the clause. I claim it's blocked for X with respect to this formula. You just need to look at the clauses where not X occurs. You have not X, not Y, but the result would be tautological because Y and not Y occur. Here, it would be tautological because Z and not Z occur. Here, you don't need to check anything. Okay, so the simple syntactic condition, which you can obviously check efficiently, even if I didn't tell you what this X is. And here's why these things are redundant. So I claim that, thinking back to the characterization that I've shown in the previous slide, if an assignment sets X to 1, then it is a witness, so that I can invoke the previous lemma. But why does it have to satisfy this? So just take some total assignment alpha that satisfies this side. It means that that alpha satisfies this and that alpha falsifies this. Now I claim that the right-hand side here, this gamma and C, is satisfied by the composition. And this composition is, again, as in Jakob's talk, apply tau first, apply alpha later, which is just alpha with alpha X flipped, because alpha was, since C includes X, was assigning X to 0. Now it's assigning X to 1. Okay, now C is satisfied, but how about gamma? So there may be some clauses in gamma whose satisfaction depended on X being set to 1. I claim those are also okay because there is some Y in C prime, which is the part of the C without X, such that the negation of Y is in B prime. But since alpha was falsifying C, then it still sets this Y to 0. So nothing is broken. Like you had a backup literal, which already satisfies clauses of this form. So what you've done is you've exhibited that if there's a satisfying assignment to this, then that assignment satisfies this entire right-hand side. Okay. And you can now generalize this in various ways. I'll show you 2 of those. Apologies for the name of this. I did not pick this. And this asterisk is for people who might have already seen this definition. This is different than the definition that you're used to, but it gives a polynomial equivalent proof system, and this is simpler, so I like it better. And everything is the same in the definition, except for this requirement. So you say, here, this is tautological. Here you say, this is subsumed by gamma. And subsumed means that there is some clause in gamma of which this is a weakening. Okay. And the intuitive way to think about this is these are saying without loss of generality, where the justifications in the case of block clauses is local, because it cannot look too much in gamma, aside from the clauses that include not x. But this here you can look anywhere in gamma to find a reason why you're good. Okay, so this is one axis along which you can generalize the proof system. You can go up. Okay, so this is maybe a little bit more complicated notion of a set block clause. Here, instead of this x being a literal, it's a set of literals. And again, you have this extra condition, which is kind of like this, generalizes this, and this extra condition, which is kind of like this. Okay. Again, do not completely try to parse this. Just look at the shapes to see that this is indeed a generalization. Because if this was a single literal, this would be the same, like set block clause with a single literalized L would be a block clause. Okay, so now we have proof systems using these notions built on top of resolution. Okay, so resolution and extension gives you extended resolution. BC is resolution plus blocked clause addition. BC minus is BC without new variables, which means that the newly derived clauses cannot include any new variables. So these are a weakening of extended resolution in the sense that this is a generalization of extended resolution, and this is how you restrict it back in a way that it still makes sense. And it doesn't just become resolution, it's something actually exponentially stronger than resolution, and exponentially weaker than extended resolution. And there's this notion of deletion, which again came up in the previous talks. I do not want to get too much into it, but being able to remove and add clauses makes a difference to the strength of those proof systems, because inferences in those systems are non-monotone. So in general, if from a formula you can derive a clause, if that formula was larger, you could still derive that clause. Nothing is broken. It doesn't hold, such a thing doesn't hold necessarily for those proof systems. If you had extra things, your without loss of generality thing may no longer hold. So deletion makes a difference to those systems. And you have like versions of this for RAT, SBC, etc. And like I said, SPR, I'm just naming it because it's a particularly strong one. SPR is like the marriage of SBC times RAT addition.
Where S is for SBC?
Subset propagation redundant
Oh,
set
I see.
block
S
clause.
is the SBC. Okay.
Yes.
Question.
Yes.
You mentioned that BC and DBC are generalizations. Yeah, right.
BC is a generalization of extended resolution. PR is a generalization of BC.
When you say generalization, what do you mean? Are they from a proof complexity?
I mean,
strong.
a BC proof is literally correct as a PR proof. Or an extended resolution proof where you add the clauses, add the three clauses that correspond to the extension is literally a BC valid in BC. Or similarly, like SPC, for instance, is a generalization of SPR, and SPC proof is just valid as an SPR proof. That's what I mean by generalization. So trivially, they similar.
But they're equivalent in power.
They're equivalent in power. I mean, they can generalize something. I mean, by that, it is a strict generalization in that an SPR proof is not necessarily valid as an SPC proof, but both are equivalent, polynomial equivalent to extended resolution. So like I said, we are looking at the versions without new variables. And this is like the key property, the key weird property of those systems that I'm gonna keep exploiting to get separations. Effectively, this is the technical term effective simulation, but with an asterisk, because it's not actually literally corresponding to the way it was defined. Effectively, BC minus without new variables simulates CR. And I will not define what effectively polynomial simulations are, but just exhibit it with an example. So there are results of this form. Suppose that a formula gamma has an ER proof of some size. And consider this set of variables, which are not shared with gamma. If you just attach this to gamma, then the new formula has a short BC minus proof. Well, because those are new variables, but technically they're not. Now they're in the formula. Okay, so this is like a trick. But this trick is useful. For instance, in this way, you can very cheaply separate BC minus from resolution. Yes.
So could you use this to say, let's resolve away a few variables, make up some room, and now let's let's
Yes,
simulate.
that's how one of the simulations goes actually.
Yes.
Between the versions of simulation. Okay, let me show you at least one. How do you do this? So consider just one use of the extension rule. Like I said, they're doing reputations without considering these literals are not new. So you add these clauses in sequence as block clauses. These are not quite corresponding to this because you pick up this extra not y, but for that reason you include y as a clause. So then you just resolve those away and you have the 3 clauses corresponding to this, and the rest is like the resolution steps are the same. So this is how that simulation works. Since BC minus does this, all of the systems do this. Okay. And I will tweak this set that you're including with the formula to get easy separations between all of those systems. So I'm calling these guarded extension variables. The terminology is borrowed from the regular resolution versus resolution paper, where they're actually guarding clauses. So it's a little different, but it's roughly the same idea. So yeah, I decided to call them guarded extension variables. So we will start with a formula with a short ER proof. And keep in mind this, which makes this formula easy for BC. We will now, to separate 2 systems P and Q, which generalize this BC minus, we will incorporate extension variables in ways that are useful to only one of the 2 systems. And so the idea is I will somehow guard the variables. But by guard, I mean they will not be included plainly like this. I will have some gadget-like things, though they're not exactly gadgets, but like small formulas in which these appear, but not as openly as this. And then one of the systems will be able to use these variables to simulate the ER proof as before, although a little in a slightly more complicated manner. And the other one, although these are just there, will be unable to achieve any speedup. Okay. And how you can achieve this kind of thing is not obvious probably, but here's just like a completely trivial example. So consider this formula, and suppose you're trying to add some clause that's blocked for x. So we remember the definition of block clauses, which says that clause has to clash against this clause and this clause when you resolve it upon x. But well, the only thing to clash against is y here and not y here. Then that clause has to include both y and not y. So that's a useless clause. Okay. So in this way, you can like impose restrictions on the set of clauses that are derivable within these proof systems. I had a example lower bound in the simplest case to show that it's in fact that easy if you're used to those systems. I'll just show you how short it is. Okay, there are like some lemmas here. Some steps are lemmas, but this kind of a formula, which is basically a generalization of the example that I've just shown you, is no easier than the original formula gamma for this VC minus system. And proving a lower bound is, and VC minus is really weak, so that's why it's so short. But still, this is quite easy compared to, for a lower bound at least. And actually, this kind of a formula ends up being easy for rat minus. So this is, for instance, the construction that we can use to separate rat minus and BC minus. Why it's easy, I cannot get into right now. But I will show you the constructions that I use to separate all pairs of those systems. Just I will flash them, and then I have a few minutes, and I will move to discussion. So. And you actually have a real economy of constructions in that using a single construction, you prove that 2 systems do not simulate this system. And one thing that I want to emphasize about this approach is, so this formula, this new formula with the new variables becomes easy for rat minus regardless of whether gamma is. So you take any formula that separates rat minus from ER minus, from ER, and you plug it here and you get your separation. Okay. Then you only need to think about how to construct it. There's a different kind of construction where you have like multiple literals. This just says x is equivalent to yi. Well, rat for some reason is unable to make any use of the x's and y's here, but this formula ends up being easy for both of the other systems for different features. And okay, SPC is possibly the most interesting system among the three. So to break it, you have to work a little bit more. And then you have this kind of construction where X is supposed to be the new variables that are to be used. And GER can just work through all of this and use this X to derive the extension clauses. SBC looks at this and says, I cannot do anything unless you give me exponential size. Okay, so using these kinds of like cheap tricks, you can separate all of those systems. And yeah, I have a few open questions. So SPR minus, going back to this picture, this is like the frontier in terms of lower bounds against all systems, because this is known to be not polynomially bounded. So is this, and so is this as part of this work. And these are probably really hard to prove lower bounds against. So that leaves SPR. So SPR minus is the system that Buss and Thapen formulated most of their upper bounds in. Some of those upper bounds hold in SPC minus. I don't know if Antonina is here, but Antonina was talking about differences in encoding between proof systems and like the same tautology being easy and difficult on the different encodings. For instance, here for this system, both the pigeonhole principle and the bit pigeonhole principle are easy. For this system, pigeonhole principle is easy, but bit pigeonhole principle is hard. And here, if you understand the once you understand the definitions of those systems, it makes a lot of sense that this is the case, because this system is unaware in its justifications of the entire formula, but bit pigeonhole principle, in a sense, is meaningful more globally, right? So subsets of it are a little less meaningless, are a little more meaningless than the unity pigeonhole principle. So yeah, this is like the frontier in terms of lower bounds, and we want separations using natural principles, as everybody said. And the third is about connecting the study of those systems to the rest of proof complexity. So right now, those are like niche and kind of new systems. So they're disconnected from the rest of proof complexity. What we know, for instance, is any system that's closed under restrictions does not simulate even the weakest system, unless that system also simulates extended theta. So that's known. But I'm more curious about the converse kind of results in that. So this is standing for the strongest versions of those systems without new variables. Is there any subsystem of Frege strictly above resolution that you can simulate in those systems? Like, you get anything, or are they completely incomparable with the rest of the systems that are commonly studied? And I like this idea, although it's a hack. I would like to see like other uses of the high-level idea. I have one idea where this can be used. And if you've heard of it, it's linear resolution versus resolution, because the linear resolution has some weird properties that are similar to the systems that I've talked about. So potentially it could be applied to separate those, which is, I wouldn't say a long-standing open problem, but an old open problem. Yeah.
So questions?
Yes.
Effective simulations, which of those incomparabilities to
effective P simulations in the original. So
yeah,
the difference from the version that I have is it doesn't have to run in polynomial time. So in the original effective simulations, it has to run in polynomial time. In this case, since you don't know how many extension variables you need to put, this doesn't run in polynomial time. So I actually don't know. So these probably do not simulate ER in the sense of the correct definition of effective simulations. But you asked about separations across those systems.
Yeah. Because lots of flavors of resolution collapse together under effective.
They, based on some of the existing results, they may end up collapsing because there are simulations where you allow just one extra variable and then you can simulate things, but that uses deletion. So I'm not completely sure, but I would guess that they should collapse.
Other questions? Just a quick one. So res2. So are there separations? Can you prove that res2 can't be simulated by some of these systems?
So the only known lower bounds are for So pigeonhole principle is hard here, but it's also hard there. Bit pigeonhole principle is hard here, but it's also hard there.
Res 2 means clauses with terms of size 2.
Yes, exactly.
And it doesn't fall from many norms of my norm.
So an easy formula for REST2 is the clique-coloring with very big gap between the.
Clique-coloring is easy here and here. SBC minus. So clique-coloring is here and here, because you can say without loss of penalty, the elements, the first, second, third, etc. element of the clique is colored 1, 2, 3. So that is expressible here and here. Yes.
If you would like to write a solver, a practical solver, which one of this language do you use? I mean, to have something that is efficient with strong heuristics and
there are some solvers that.
I'm not telling you.
Okay, so Marijn and Armin and Mayim actually tried to do this, but the difficulty is you need to compute the difference.
yeah,
And even if you claim the formula is,
it's only working on Pigeonhole, right? Or
yes, but
But
this
in
is also
practice-
good. So I like this as well.
this one?
Yeah.
So you're talking about the satisfaction-driven
Yes.
clause learning. They use some version of SVC or SVC minus, I guess,
Oh.
in their thing.
So not SPR.
No, I think it's a version of SVC minus. Okay.
And it makes sense. This is here hard. But as far as I know, that only works in really specific cases, right? It's not like it's uniform including or, you know.
It's machine learning.
Well,
So, but it worked rather well for certain types of pigeonhole principle. Let's say it that way.
yeah, but extended resolution also. I mean, we have
But here it's like a better guided search. You don't have to look for a new error.
I can say that we have tried to build an STCL solver, and it works well for certain kinds of problems, but not other kinds of problems.
Yeah.
And one of the issues that we face there has to do with the branching rules.
So if you, I mean, the source code for this SDCL solver is online, and I had a couple undergraduate students ran it last quarter, and they were able to get the same results using their software, of course. But when they used randomly permuted versions of pigeonhole principle, it didn't work. The variables, yes, they were permuting the variables, yeah. But we didn't explore what's going on, so I don't know what the fix is or either.
So in that particular solver you're talking about, they use a
cat-cal solver, yeah.
they use a very particular branching heuristic that's kind of tuned for pigeonhole.
Okay, well, yeah, we didn't get into the innards of that. So I think there's, but it's interesting, they're able to find more or less the optimal pigeonhole principle refutations of size around n cubed up to over 50 pigeons, which is a pretty amazing number.
Oh, and on that note, one more thing. So the system here that's just outside, like that's here, called PR, that actually has short proofs of Russell and Polyasso's example from the first day, which related chess, which is hard to see. Yeah. Okay. So that's also like a more interesting.
All right, well, let's thank Emre again. And don't